In this video, we're going to continue with this differentials idea. And just before this, we used a method very similar to Newton's method to approximate a function at any point, not just the zeros. And so we had to go about it a slightly different way, but it was similar in nature. And so we approximated the function using a tangent line. And we said, well, you know, as long as we're close, if we're close to whatever x value we're talking about, the tangent line's pretty close, or at least we can get it as close as we need. And so now we can use the tangent line to achieve a new level of accuracy, something that is termed the differential, or the differential change. And so if we call x minus c the change of x, then y can be approximated by and y is equal to this, which is f of c plus this change of x. And then we subtract off what it already was, and so that just leaves us with our change. Then the change of x can be approximated by f prime of c times this change of x. Now this is when the change of x is sufficiently small. Remember, we got a better approximation from our previous examples. We got a better approximation when we were closer and closer to the actual number that we wanted. And so we can use these to achieve different levels of accuracy. Now, as we go through this, you can think about, let me just try to draw an example here. Okay, let's get an x-axis in here somewhere. Now, this isn't necessarily any particular function, but this is just for illustration. So if we have some value here where we have the tangent function, this is at c, and we move, okay, so we're going to move a little bit over here. Well, this point that we move at, or this distance, is going to be the change of x. Okay, so this is going to be, this here is f of c. This is going to be f of c plus delta x. I just screwed this up. This is not f of c. Goofball. I'm sorry, I apologize. I had my drawing right in front of me and I still screwed it up. Okay, right here, this is our f of c. And this is our f of c plus x. And now if we look, this point right here at this some point c plus delta x, this is our f prime of c change of x. Okay, so this is our tangent approximation. It's getting pretty close. Now suppose we get it closer and closer and closer and closer. Okay, so we shrink this delta x. In effect, we're going to move a little bit closer, and then a little bit closer, and then a little bit closer. And you can see every time we go closer, the distance here between these two shrinks until we get so close we can't tell the difference. So if we let our delta x tend to 0, then our delta, our y value then y will tend to f prime of c delta x, or a change in y, I should say. Okay, when that happens, we call this a differential. This is a differential of x. This is the differential of y. And so the way that we have this is that dy is equal to the derivative at x dx. Okay, so how much y changes depends on the slope of the function at that point and how much x changes. This is assuming that x is kind of squeezing down, that this difference in x is squeezing down to 0. And so if you're talking about big changes in x, you can't use differentials. You need little changes, little bit of changes. Another way that students kind of remember this is, we talk about taking the derivative. And so if we have a function here, some f of x, then we could take its derivative, which is f prime of x. But at the same time, if y is our function, its derivative is dy dx. So one way to look at this is dy dx is equal to f prime of x, which means that dy, if we multiply both sides by dx, is equal to f prime x dx. Okay, that's one way to kind of remember it. I don't believe that it's actually as true as that, but it is what it is. I mean, we're saying the differential of x is going to be a small number, and we can still multiply both sides by a small number. And so it approaches it in the limit. So this is really what we're kind of getting at, is this idea of as we squeeze down, as we approach this magical value c, we're going to get a better and better approximation of that. And this is our better approximation right here. dy is equal to f prime of x dx. Okay. Now we could use these differentials to determine errors. And that's kind of the logical next step, is it really is in our best interest then, if we're approximating this, then we want to look at the errors associated with that approximation. And that's what we'll continue on with the next video.